And thank you for the invitation to be able to come and present to you today. It's my first time at the conference, hopefully not my last, and a privilege to be here. As was said, I'm Andrew Smith. I work for Bentley Systems, and the first question I always get asked, nothing to do with the cars. We're a completely separate company who focus purely on software for civil infrastructure. So the presentations I'm going to be giving today, we're not going to talk about rolling stock or signaling systems. It's just civil infrastructure through the asset lifecycle. I'm going to split my presentation into two parts. The first thing I'm going to be talking about is the challenges and opportunities that change actually gives us. And there are many different varieties of change that I'll go through quickly and we can talk about. Then what I'm going to do is work through the rail asset life cycle, trying to show some of the benefits that digital transformation has already delivered in other organizations around the world, in other rail organizations around the world. Just quickly to give a flavor of who Bentley Systems are, for those who don't know of us, we were established just over 40 years ago as a pure software house. We currently have over 5,000 colleagues spread around the globe. We're used in well over 100 countries, and we actually invest heavily in research and development for ourselves as well. So $750 million over the last 3 years in research and development, purely into software technology. We do focus on more than just rail. We focus on all civil infrastructure, so rails, roads, mines, ports, dams. Okay? But the focus for today is just going to be rail. So the sorts of challenges, firstly, environmental challenges and the background to us. We've got changing environment that is actually causing us issues inside our infrastructure. We have aging infrastructure that we need to maintain and keep safe and fit for purpose. We have changes in the way that transportation is being used globally at the moment as well. And we also have changes in the ways that people are working. So what we can't do is consider that the requirements we have from our transportation infrastructure are static. They're constantly changing, constantly evolving, and we need to actually keep up with those changes going forwards. One of the big challenges we have. Now, if we look more microscopically at transportation in particular, there are a number of specific challenges that we actually see here. The first is actually this growing demand, the emphasis, and the investment that's in place. So we're actually finding that sustainability is becoming far more critical. It's a higher profile that we've got, especially as we're seeing more change over time as well. We're seeing the way that funding is taking place is evolving as well. So we're seeing more public-private partnerships coming in turn. If we look at the complexity, the engineering complexity, in particular for the construction, the design and construction of our systems, we're building a lot of metro systems that are going through existing infrastructure. And as time goes by, our cities become more complex, those projects become more complex as well, and the implications and the impact they're going to have as well. There is also less tolerance for overrun in time or cost associated with these projects. So we're trying to make sure that we're delivering more complex projects on time and to budget. We're working more and more with data. So we're moving away from just using kind of engineering intellect and pen and paper to building data that represents the use of the systems, the plans that we've got, the models, the designs that are in place, the construction sequencing, everything. That data has a horrible habit of being fragmented across multiple organizations, fragmented through the supply chain, and fragmented through the life cycle. This data can be hugely beneficial if it actually gets centralized and can be reused throughout the asset life cycle in turn. But this causes all sorts of challenges in terms of intellectual property, file formats, the standards that we use that are in place, and even contractual frameworks to make sure the right data is delivered so it can be reused further down the asset life cycle. And finally, I'm talking globally here, as I'm not an expert on tie rail, but certainly globally, there are huge challenges in terms of getting the right quality skill sets, the right people to be able to help us with the projects that we're delivering. Globally, as you can see, 33% of all engineering roles are unfilled at this point in time. There is a shortfall of over 400,000 quality engineers to help us with the transportation projects that we're working on. So given the amount of growth in rail we're seeing around the world and in this region in particular, we cannot throw resources at it. We can't simply work harder. We have to work smarter. The other thing about the numbers you see here is they mean if we can be more efficient through digital transformation, it does not put engineers at risk in terms of the job, the work they're doing. It means that the engineers are actually able to deliver on all the promises that are coming down from the senior levels in the organization in terms of growth of the network, increases in efficiency, use of transportation for freight and the like as well. So the next thing we're going to look at quickly is some of the challenges that we see from a technology perspective. And these double up as opportunities because they're things that are changing. So we talk about digital twins. And a digital twin I'll talk about in the coming slides. It's just an electronic representation of a system or process that you have, which is it's not just a kind of a pretty picture. It's what is there, it's why it's there, it's how it got there, and it's kept evergreen so we can ask questions of this twin in turn. And it brings together all of the data and information we have related to that asset. Cloud computing is very much the way that a lot of technology is going at the moment, so centralization of storage, centralization of processing, which allows us to manage the huge volumes of data that we're actually seeing in terms of systems we have. Artificial intelligence, my background is actually not civil engineering, my background is artificial intelligence from 37 years ago now, so I've seen the evolution right the way through. The last 6 or 7 years has seen an explosion in terms of the capability, the art of the possible in AI, led largely by the changes, the step changes in the hardware and the ability to process these massive neural networks. Internet of Things, devices that measure and talk to people or to other devices, already outnumber humans by about 10 to 1 on the planet. That number is going to increase going forwards as well. All of these devices collect data. They do not collect information. Engineers do not need data. Engineers need information, which is that data in context. And then finally, geospatial technology, the likes of Google data, satellite information that can give us the big picture context. I would suggest all of these technologies combine together to give us great opportunities. Cloud computing acting as the central storage that can cope with the scalable, the volumes of data we have. Digital twins to act as the framework that allow us to bring all the data together and see it in context so we can turn it to information. AI allows us to actually connect to that digital twin and understand the relationships between data, the trends, deteriorations, and help us to make more informed decisions. Internet of Things is keeping that model current so that we're not making decisions on out-of-date data. And the geospatial gives us the big picture vision in terms of what's happening, not just on our corridor, but the environment around it as well. So if we take advantage of all of these technologies and the relationships between them, we can introduce a step change in terms of the types of decisions that we can make and the confidence with which we can make those decisions as well. Just quickly, for those who aren't familiar with the digital twin term, I saw quite a lot of nodding when I mentioned it, but there are a few who may not be aware of them. A digital twin, certainly from Bentley's perspective, we're actually combining data from multiple sources together. So there's going to be survey data, design data, requirements potentially for how a system was built. Usage data is coming for railways. It's going to be tonnage and vehicle movements that are in place. And also the demographic data we heard about previously would actually fit into this as well so that we can run models and understand what's happening in our rail networks. And then combining that with measurement data, with the asset register, and with bits of information like, for example, the work history that's in place. All of that brought together helps us to make more informed decisions about how we use, how we maintain, and how we need to change our rail network so that it actually aligns with the changing requirements that we've seen in terms of the industry that we work in and the world that we're supporting and delivering against in turn. So that was the first half, just looking at change and the issues there. What I'm now going to do is run quickly through the asset lifecycle, looking at some examples from around the world of places where people have gone through a digital transformation process in rail and transportation and actually identified some value that they've received out of the far end. So we're going to go through planning, design, construction into operation. This is by no means comprehensive. If I was to try and cover all the asset disciplines, all the regions, we would be here for weeks, months covering through. So it's just a kind of a thin snapshot. The first example from planning, I'm nearly going to skip over it because it actually very closely aligns to the presentation that was given previously in terms of looking at urban planning and looking at the optimization that's in place. The only thing I will say here is that this is an example, it's actually a smart city in China example that was put together. And what was done through looking at multimodal analysis, so looking at how people are using all the different modes of transportation, both with the current infrastructure and proposed infrastructure, and where people are traveling from, where they need to travel to, how you can actually minimize the carbon footprint for the travel that is going to take place that's in turn. And the numbers they've come up with there is improving travel efficiency, so reducing travel times by about 15% on average, and reducing vehicle carbon emissions by 21,000 tons by putting a framework in place that encourages more efficient transportation that's in place. Reducing that travel time actually has huge knock-on benefits as well, because time that people spend traveling from home to work, back again, things like that, it's effectively dead time. They're not producing anything, they're not consuming anything that's in place. So if we can reduce those travel times, people can actually become more productive in turn. Although I do accept the question that came through previously, I'm not talking about the kind of the relative value side of things, just that the analysis can actually come in and be used to tell us the impact of the changes that you're having that can potentially be beneficial and detrimental to allow you to make these bigger picture decisions about where we should be going with our cities and with the infrastructure that supports them. Another example, I know we have some colleagues over from German railways, so I think I'll use an example from here as well. This is a case, the video incidentally for those who know German railways doesn't match the project exactly, just to say that. When we talk about digital transformation, we're not just talking about what's happening above ground, there are challenges underground as well. 50% of all transportation projects are detrimentally affected by geotech issues that are in place, unknown, unexpected geotech issues. Deutsche Bahn were actually building a length of line, and a significant portion of that line actually had to be put underground because they were going through areas of outstanding beauty, areas of scientific interest, so they had to minimize the environmental impact. The challenge they were going through multiple strata of different kinds of rock formation. So they actually put together running boreholes, LiDAR data and the like to understand the varying geology underneath the mountain ranges they were going through, so they could optimize the designs that were put in place to actually be able to deliver the system. What I hope will happen from here, and what we try and stress to people, is if you've collected that survey data in the design phase or in the planning phase, pass it through the construction phase and into operations. So when you're looking at asset deterioration over time, you can actually refer back to the information that you collected right at the planning phase, and it might give you an indication of a geometric issue that you're seeing could be a result of going through two different types of terrain subsurface. Now we'll move on to design, and rather than looking at individual design tools and design platforms, what I'm going to focus on is design integration. So this is an example from the UK, from High Speed 2, where what they've done is collected together in a single dashboard all of the projects, all of the contracts that are in place for the entire system, so 200 miles of high-speed line and all the associated infrastructure, and integrated it together so that you can go into one dashboard and look at the current state of the entire program that's in place. So this is allowing us not just to look at the current state in terms of the contracts that are in place, but it's the deliverables, it's incidents that have taken place, it's spend that's taken place, it's the assurance process and how that's progressed through. And even being able to go from all of this information to say, I would like to drill in and look at the current state for a public inquiry, for example, we can just open up online a view of what the current design looks like from all the different asset disciplines and allow us to go in there and communicate that information out clearly. In order to be able to do this, one of the key things that happened was standardization of data, of naming conventions, taxonomy, asset hierarchies that was mandated down through the supply chain so that they could deliver data back in a consistent form to enable this level of integration to take place. But they'll get efficiencies, well, they're getting efficiencies now, but downstream as well, in terms of being able to hand over a consistent representation, a digital twin of the entire as-built system at the tail end. Another example, slightly closer to where we are now, is from Indonesia. We're looking at the Jakarta to Bandung line. They used BIM methodology, so they actually had a collaboration mechanism for the design that they did that made the supply chain work together and be able to share the information that they needed in line with ISO 19650. As a result of the process they went through there, they've reported that they've saved about $185 million and shortened their shortened their design schedule by about 6 months. So it's making significant differences. The reason this is happening is because if you've actually got that collaborative mechanism, a consistent way of working through design, there is less risk of rework taking place, clashes being identified too late in the process. So they've actually improved the quality assurance by 40%. It's still not perfect, but they're actually increasing the reliability of the deliverables that they get in turn. This is not a project specifically, but this is identification of trend. One of the things that we're seeing more and more is that carbon footprint, and in particular embodied carbon in designs, is not an add-on. It's not an also-ran that's sat over to one side. It's an integral part of the requirements that are in place. So what we're doing at Bentley, we're actually embedding the ability to actually log and capture the embodied carbon that sits inside any of the different design schemes that you've got so that you can generate those reports. And that's done in conjunction with systems such as EC3, the industry standards that you use for actually identifying and tracking captured carbon. We'll move from here into the construction world now, and we're jumping over to Australia. So the example here is actually from Melbourne, level crossing removal. What they're trying to do here is actually remove level crossings, but every time they shut down, they actually have to shut down the road and the rail network at the same time. So it's doubly disruptive to the environment, especially on top of existing infrastructure. So what they've done is built a digital twin to the minute of every single piece of work being done, where all of the cranes are, where all of the lifts are, where all the deliverables are, where the positions of safety are from minute to minute through the project as well. That's actually linked through to systems on site, so if they identify any problems or changes, they can get fed straight back to the central office, identify the impact on the critical path, update the project in turn. So when they do their daily site briefings, the daily site briefing is based on the actual current state of the project rather than a generic briefing of where they actually should be against that project in turn. And so again, the attention here they've got is actually to cut down the modelling time that's in place, but also reducing carbon footprint by increasing efficiencies in the way that they're actually working. We'll move from here into operations and maintenance now, and there's a couple of examples to show. The first, again, from Australia. So what we're looking at is a digital twin example that spans a range of different types of data. The first one we're seeing here is actually what we call a reality mesh. So this 3D model that you can see is actually created from drone images. It could be created from drone images and LiDAR if you had the data available. And that's then geo-referenced so that we can dimension, measure, look at positions of safety, access and egress. But then they've superimposed layers of data on top. For example, ballast condition from ground penetrating radar, so that we can actually understand if we're going to do maintenance, what's happening underneath the ballast. They've put in all of their capital project work, so you can look year on year where they're planning to do capital changes to the network. So where they're planning on changing switches, they're changing the geometry that's in place, so they can understand what's coming up in the future, and they can even potentially update the model from there. Pulling in their track geometry data so they can see how ride quality and derailment risk is changing over time and how maintenance work has actually impacted those risks as well in turn. So we're starting to bring together multiple data sets to represent the twin. The next sample data that we're looking at is actually pulling in point cloud data, LiDAR data, and then pulling in 360-degree imagery. But all of this is referenced against all of the other data sets that are in place, which means if you pull up one of these images, rather than just a dumb image, it actually understands its place in the world. It understands its relationship to the other data, which means we've got the ability to go in and start doing annotations, tagging, validation of data, kicking off workflows straight from the video to be able to identify whatever we need to from that system, integrated in, again, with everything else we see. And this view, in turn, integrates through to LiDAR data as well, so we can see the point clouds where relevant. What we would then do in the same system, they've actually got all of their possession work, their possession plans, and any annotations that have been made by engineers who've been on site previously. So I can actually go out and do literally a virtual site visits in place. I can go and look at the physical site that's there. I can look at the video from the site. I can look at the asset register. I can look at the possession area that's in place. I can look at any records or notes from the users that sit there. And then I can even cross-reference that through to, for example, GIS data. So if you have a GIS system, you can pull in all those GIS data to give you the geographic context that sits around the region where the work is actually taking place. And finally, in the system that's been set up here, they've got the ability where they have BIM, well, I'd say, I don't like calling them BIM models. It's BIM, so CAD models that have come through BIM processes, because BIM is a process ultimately. We can actually pull that data in as well and actually see the design environment, but we've consumed all of the intelligence. So we've got all of the metadata in as well, which could link through to requirements, to standard documentations, maintenance records, things like that. One of the things I would note about a system like this is if you try and build this in one go, it can cause huge problems for you because there's so much data that you're actually trying to track and trying to manage. So one of the best ways to do this is to build your digital twin incrementally based on the data that you have by dimensions of data and by where the value is going to be. So you can build that system, put some data in, gain value from changing your process to do that, and then build incrementally on from there, rather than just trying to do the whole thing all in one hit. Another example here, we're going over to the US. This is actually Robert Street Bridge. And what they've done here again is a drone flight. It's a historic bridge, so there's no design data associated with it. It was designed on vellum, I would assume. We're looking back 100, 150 years, potentially. So what they've done is actually scan the bridge, and then they can use either virtual reality or they can use just a plain screen to be able to go in and visualize the bridge itself. As well as the benefits of reducing the amount of time it takes to do an inspection of the asset that you've got, one of the key advantages I see to this is that if you don't have a digital representation, you're not transforming digitally, you can use something like this as a baseline. On a named date, this is a digital clone of the physical asset that was in place, and we can then track that forwards as well. So you can use this as the start of your digital maturity journey. What they're also doing is running AI on top of this to do things. Currently, it's for crack detection, so it's been trained to identify cracks in concrete. It's not making decisions for the engineer, but it's identifying areas and prioritizing those to say, these are the areas you should be looking at first based on length of crack, width of crack in turn, and you can prioritize those and go in and try and understand what it is that you're actually looking at in turn. Going forwards, they're going to do subsequent scans of the bridge, and the power of those is you can go and identify a feature or a defect and say, what's changed, what's happened, stay at the same place and zoom yourself back in time to look at the earlier version in turn to understand how changes have happened. The system also supports IoT feeds for live data coming in and other forms of analytics, but we don't actually have those in the example. Again, what they're finding from using this technology compared to the traditional way of abseiling or cherry pickers over the side is reducing the total effort to be able to do the inspection by about 30% through use of technology, which is useful because when you have a large number of bridges and a smaller number of bridge engineers who are trained to be able to do these inspections, they can do triage of multiple bridges from an office so that when they go on site, which they will have to do, They actually already understand the context, they know where they're going to look at, what the priorities are, so they can reduce the time they take doing the actual inspections that they need to be able to run. Now we'll jump over to Singapore Metro, SMRT in particular. What they wanted to do was go through a digital transformation of all of their asset systems to increase reliability. Their metric for reliability was MKBF, or mean kilometers between failures. When they started this project, they were on slightly under 200,000 kilometers between failures, a failure being a 5-minute delay for any reason at all. They actually transformed all of their asset systems, and we only focused from our side on the track systems that were in place. But they brought together their design data, their operational data, their measurement data, the maintenance records, and used those alongside a digitization of the amount of work that crews could do in a shift and the efficiency that they could work to try and optimize things like their rail replacement processes. And as a result of that, without increasing the engineers that they had, they improved the reliability of their rail network by about 500%. So they were on slightly over 1 million mean kilometers between failure in 2019, which was about 4 or 5 years after the system got kicked off to be able to go through. So again, demonstrating that you can get those increases in efficiency by using the engineering resources that you've got as efficiently as you can and using data to help drive the decisions that are taking place. Data is kind of the trend in all the things I've talked about here. So I would draw your attention. There was a report by McKinsey a few years ago that looked in Europe, I know it's not local to here, but in Europe, at the expected return on investment for rail operators going from reactive and time-based maintenance through to condition-based maintenance, so using data about the current state to make maintenance decisions, and they believed it was about a 10 to 15% saving in the total maintenance budget. Or you can change that to, you can do 10 to 15% more within the same budget you've got, depending on which way you look at these things. And then going from there, further on to predictive maintenance is a further 5 to 10%. From my experience, though, most rail operators around the world want to be in the fully predictive world. The reality of where many of them tend to be, even when they're digitally transforming, is they have the data to understand the current state of their system, they understand the history, and they understand the deterioration rate, so they can make more informed decisions about maintenance work, but they haven't gone to the truly predictive world. That's kind of a step beyond where the vast majority are at this point in time. So closing thoughts from my side, I'm actually going to take a quote from our current CEO, Nicholas Cummins. The focus here is that everything we've talked about is trying to use data to help us better understand what's happening, make more informed decisions about safety, usage, reliability, cost, and the like as well. The more we move towards a data-centric world, the more we are relying on data to support the decisions that we are making. And it becomes more and more critical that that data is fit for purpose. So if there's one thing that people are going to take away from the presentation I'm giving today, is the data that you have is not only data about an asset, it is an asset in its own right as well and must be treated as one. So we need to make sure that the asset is periodically monitored, so the data is actually checked to make sure it is complete, it is current, it is fit for purpose, it's not being misused for anything that's in turn. And it has long-term sustainability, so the data we're collecting now might actually not be of any use, or we might not need it for 20, 30 years, or maybe even at decommissioning. So understanding how we can store and manage that data, give it the longevity, so that it can support the sustainability of the assets throughout their life cycle. And the asset life cycle that we're looking at here is far longer than the life cycle of the systems that are going to maintain this data. So the data is going to have to evolve and flow between successive systems out into the future, potentially for 100+ years, to actually deliver a safe, reliable, cost-efficient, well-perceived, sustainable rail infrastructure. And with that, I'll pause and see if there are any questions.
Yeah, thank you very much, Mr. Smith. Any question from the audience? Oh, one from the floor.
Well, I'm not sure.
John Roberts from KU Rail. I used to work for Bentley Motors. Just as an aside, I'm thinking about Railtrack in the UK and their yellow banana, the track infrastructure measuring train. I talked to contacts in Railtrack, and they say they use that train. They collect so much data, they have no baldy notion of how to analyze it. They've gone from trying to be proactive to being reactive. So the only problems they can solve are the ones that are immediate. So they detect something on the track that's unsafe, they stop the train and block the track until it's repaired. They can't put together a program of proactive maintenance because there's too much data. And it strikes me that your system would be ideal to help them. Have you talked to Railtrack?
Yes, well, Network Rail as they are now, they've evolved forward.
Okay. I'm old-fashioned.
Firstly, from my side, before I worked for Bentley, I used to work for the UK Rail Research Institutes in Derby, and I actually worked on the Yellow Banana train for software that sits on top of it. What I will say in terms of data volumes, if you move away from Network Rail and we go and look, for example, at North America, one of the Class 1 railroads is actually collecting data from in-service vehicles. They have 8 in-service vehicles traveling 16 hours a day at line speed over their rail network. They are collecting tens to hundreds of gigabytes per day and streaming it real time into a back office. Our technology is actually supporting that entire framework they've got so that they can actually, as soon as a problem actually comes in, they can validate it, a manual process, so there is actually accountability. You don't want to completely automate that through, otherwise where's the accountability for sending a crew to a dangerous location because of a data error, for example, and then pass that through, including the type of work to be done, within minutes of the vehicle going over the system. The beauty of the process they're using is they've actually moved away from what Network Rail do, which is they actually run a 3-monthly system, which is effectively an audit of the network, because that's all they can do with the frequency they've got, to actually moving it into being a tactical decision-making tune based on the increased frequency. And as a result of that, they've managed to get the FRA, the Federal Rail Authority for North America, to reduce the requirement for inspections that they're running from weekly to fortnightly, which doesn't sound like much, but it halves the number of visual inspections they need to do, and it's a great first step to using that digitalization.
Yeah, you're right. The UK has some good systems. London Underground, for instance, use their new Bombardier trains to actually collect the data on the track and data on the trains, and it's all monitored back in Derby on a 24-hour basis. So yeah, there are better systems, and what you're doing is excellent. I loved your presentation. Thank you.
No, appreciate it, thank you. And when I talked about change, one of the things that is constantly changing is actually the art of the possible in terms of measurement systems. And indeed, one of the measurement systems that we're using, or we're just starting to look at using, is a low-cost triaxial accelerometer with gyroscopes and a GPS system known as a mobile phone. Now, it doesn't give you an objective measure, but a subjective measure of ride quality that you've got. You've got a low-cost system that you can just put in place, tape it down on a seat so that you're only getting the ride movement, run the filters against the raw data, and start identifying where you comply or where you're out of spec with the international standards for ride quality. So that's just an example, but we're continuously seeing new innovations in terms of the different things, the ways that we can measure. All of these, though, exponentially increase, exactly as you said, the volume of data. And I think you getting to this fundamental essence of what I was saying here, data is no use to you. More data is less use to you, but you need a mechanism to turn it into information by seeing it in context.
Yeah, it's not just a question of collecting data, it's a question of collecting the right data.
I would agree, yes, but this almost goes on to the research question that was asked earlier about focused research versus pure research. I have been involved in projects in the past where we've actually collected more data than we need in terms of geometric frequency, not because there was a requirement for it, but because we wanted to do some pure research. If we have 3 recording runs a day of track geometry down a piece of track, what can we do with that information? And there was no target for it at the tail end. We were just oversampling to understand the value, and it actually helped us to understand extreme deterioration rates from failed maintenance, for example, which could drive the frequency you should be running at.
Yeah.
All right. Thank you very much.
I'll stop.
We may need to talk later.
All right. Thank you very much for sharing your expertise.